Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, continuing from where we left, in this section we will be talking about optimal controller design, but also we will try to incorporate safety into the design. Earlier we have seen how to design linear quadratic regulator, which is one kind of optimal controller design technique. So, fine, let us move on. So, the first thing we need to do is we need to define safety of the system, right. If you recall, earlier we talked about barrier functions as a method, right, and we will see that how that can be used to ensure safety of the dynamical system. That is, we will not only design a control law which is optimal, but it is also designed in such a way that it ensures that by application of that control law, your system does not veer to some position in the state space which is already marked as unsafe. So, we will use this simple example of harmonic oscillator whose these parameters are given like this. So, this is the equation of the harmonic oscillator in a continuous dynamical system form. So, again we are doing the analysis here in a continuous time space, but similarly we can also do it in the discrete space. So, and this is the overall domain in the two dimensional space. So, this is your domain, and you can see that this is marked in this space, that we want that both the x1 and x2 variables to be always being positive. So, in this coordinate two dimensional coordinate system, we are having this green part as the domain of the system. Okay. And we are saying that, well, the system may start from an initial state space which is like x2 equal to 0. So, you will always be on this x1 axis, right, and x1 initially is between 1 and 2, right. So, that is your initial state space. That means, the system can start from anywhere on this yellow line here. Okay. And then we say that, well, we have an unsafe region in the state space, and that unsafe region is given by this set of linear inequalities here. So, let us figure out what are the unsafe regions. So, what we are saying is the unsafe region is x1 less than equal to 2. So, this is x1 in this direction less than equal to 2. So, it is bounded by this line here, right, and then we have x2 less than equal to 2, right. So, x2 is increasing along this axis, right. So, you are bounded by this line here, and then we have x1 plus x2 greater than equal to 3. That means, we are saying that, well, any location on this side of the line, on the right side of this line, right. So, since these three are conjuncted, so overall we have this red marked region as our unsafe region specification here. Okay. So, what we want to do is we want to design a controller which will steer the system towards stability, and additionally it will also ensure that, well, the system never reaches this thing. So, if you see the difference with our earlier mechanisms, earlier we just designed controllers which were optimal with respect to the control objective, and the control objective was trying to minimize the deviation from the equilibrium point, and also the control objective was trying to minimize the amount of control effort that is there, right. But we are saying that, well, it does not guarantee that the system will never be unsafe, right. So, how do I also make that control objective sensitive to this kind of a safety specification? Okay. So, we have a safe set here. The safe set is this d minus u. U is my red colored unsafe region. So, this is my safe set. So, what we need to ensure is this, that the safe set is an invariant. Now, we can understand what it means as an invariant, right. It means that, well, let the system at some time t1 belong to S. That must imply that for all t2 that is greater than t1, the system x at t2 must belong to S. So, this is the invariance condition, right. And also we have an initial state. That means, we are assuming that, well, the initial state is definitely in the safe set, and not only that, I mean, if I start from the initial state, eventually I must reach this thing, that eventually at some t1 greater than 0, well, I am still in S1 and then I continue to be in S1. Okay. So, this is my requirement. Now, let us see, I mean, what are the techniques to address this requirement, how do I justify this requirement. So, for this we will use our earlier definitions of barrier function. So, we consider a barrier certificate candidate, right. We have to if you remember, we need to create a barrier function and we have to prove that, well, this is indeed a barrier function for this system, or we have to show that, well, if something is like a formulation for defining my control law, then the control law is such that it always satisfies this barrier function, right. So, if you the difference between our earlier and right now method is that, well, earlier we said that, well, suppose you are given a system and you are asked to prove that, well, the system is safe or unsafe. We said that, well, the system is safe if a barrier function exists for the system. So, we took some candidate polynomials and we tried to show that, well, this is indeed a candidate barrier function or a valid barrier function for this system, and since I can define that, so the system is kind of safe, right. But now the requirement is a bit different. We are trying to say that, well, we will create a candidate barrier function which kind of justifies that, well, this is indeed a barrier function because it does not contain the unsafe region of the state space, and we design a control input, so that with that control input the closed loop satisfies the barrier. Okay. So, let us see. So, let us consider our same older barrier function, if you remember, which was this x1 square plus x2 square minus 4.3, something like that, right. So, if you try to create the 0 level set here, it will be a circle like this, right. It will be a circle like this with radius equal to 4.3. Okay. Now, the idea is that, well, all the points I mean on this system. So, this is like a phase plot, right, because essentially we are plotting the values of b x1 x2 as a function of x1 and x2, and the values of b are all defined on this blue shape, right, on this blue kind of cylinder which is slowly tapering down, right. So, that is the shape. So, the values of b all lie on the surface of this, right. It can move around like this. Ignore these black lines here. They actually represent the the way the function's value will go, but it will always be on this surface, right. Now, the thing is, this is my 0 level set. That means, if these are the combinations of x1 and x2 for which this function's value becomes 0, and since we want this to be a barrier function, that means the function as long as I am inside the barrier, right. The idea is that we need to show that, well, for the system inside its safe region, it is always operating with the value of b less than 0. That means, the system's safe trajectories are all located here, right, on the surface of this cone, but those positions which are below this 0 level set on the surface here, right. Now, if you remember that, why is this a valid barrier function? Because, well, see, ideally we could have allowed the system to go here, here, everywhere, but not here, right. We are taking a subset of this allowed safe set and creating a barrier function in that subset, and we are saying that, well, that is my requirement, that the idea is that, because I am free to choose the subset, as long as nobody is telling me that, well, why your subset is small, it could be something which also captures this, but at the same time then it may not be a continuous convex shape, right. So, as long as I am here, it is still safe, right. As long as I am below, it is still safe. Now, the way we design it is that, well, if we cross this 0 level set, if we go to some points here, here like that, then what is happening is, see, maybe this thing is like beyond this boundary, the safety boundary here, right. But if I cross this barrier, it is possible for the system's barrier, it is possible the system will reach such values of x1, x2, so that it comes to the unsafe set. But what will also happen is that, suppose sometime I am coming at positions here. If I come at any position here, correspondingly the barrier value is positive here, right. So, that is the trick of the barrier function, if you remember. The moment I come somewhere here, it is beyond the 0 level set, right. For the 0 level set, the x1, x2 values are all located here, right. The moment I come here, the values of the barrier become somewhere here, right. That means the barrier function becomes positive, and that is how we define the barrier function. That means that the moment I cross this, the system is like crossing into the unsafe region. Let us note one thing, I may be here, it is not unsafe, I may be here, it is not unsafe, but we have conservatively defined it. What I mean by conservatively defining is, let me just repeat, we are saying that, well, this entire green is safe, the red is unsafe, but let me take a subset of this, what we call as safe, to be really safe, which is this part, which is basically this part, we are considering this part to be really safe. And we are saying that, well, everything else is unsafe on this side. Okay. That means now my system can start here and then it can go anywhere here, but it is never allowed to get beyond this 0 level set, because let us understand, if I get beyond this 0 level set, I am also allowing the system to climb to this kind of positions, and if I climb to this kind of some position here, right, then the corresponding x1 and x2 values, if you take the projection, let us say the barrier somehow I allow it to increase. If I allow the barrier value to increase beyond 0 to a positive value, it is possible that I will come here. If I come here, that means the barrier value is coming here, that means the corresponding x1 and x2 values are here, right. So, it becomes unsafe. So, we make a subset of the allowed safe region to be my safe set, and we make a superset of the allowed unsafe region to be unsafe. That means everything here is positive on the top, right, on the super level sets. So, essentially the 0 level set is the safety boundary for me, and the sub level sets, that means positions which are below this, where the barrier is negative valued, those are my safe regions, which is perfect, right, but I do not allow it to come anywhere here. I do not allow the barrier to grow anything here, because if it grows, then it becomes possible for the real system to come here, right. So, I hope this becomes a bit clear now. So, this was my barriers definition, and satisfies the classic barrier definition, that it is negative and it is 0 at the boundary, and it is positive if I ever go to unsafe region. So, that is how the safety is defined as an invariance, right. Now, what we want to do is we want to design the controller which respects this barrier, right. So, let us consider this generalized dynamical system, x dot equal to f x plant equation plus g x u. So, this is the controller's input u, and f and g are globally Lipschitz. U is the control input, it can be an M array input. Okay. Now, for this B function to be a valid barrier certificate, now let us notice one thing, I am trying to define it for the closed loop, right. That means it is not only defined over x, but it is also defined over u, right. So, my requirement is that the control design should be such that the value of u belonging to the set of possible control inputs is such that this barrier's value defined over x and u is negative, and not only that, its gradient is also negative, because let us see that automatically will ensure that my safe set is invariant, because if barrier is negative, that means by definition of the barrier which was defined with respect to a safe set, I am inside this safe region, and since the barrier's derivative is time derivative is negative, that means I can only decrease. So, I can go here and here, but I cannot go here, and since I cannot go here, since I cannot come to positions like this on the surface of this cone, I will never be, I mean the values of x1, x2 cannot be from this red region. Let me just repeat what I just said. So, we are ensuring by my design of the barrier that initially my barrier value is negative. Okay. So, if you put the value of x1, x2 0, you will get minus 4.3. So, let us say I am here, the barrier is somewhere negative, then you have this initial set. So, you can start anywhere inside this, you will see that for all values of x1, x2 inside this barrier's value is negative. So, you will be in the sub level sets, okay, and then you can climb up here, but you are never allowed to go beyond this. Since you cannot go beyond this, you cannot come to positions which are like, if you take this boundary, right, if you draw this projection here like that, right, you are unable to come to positions here of the barrier and since the barrier's value cannot belong here, that means the system cannot come here. Okay. So, that is how it works. Now, the thing is we want to design the control so that the barrier's value is satisfying these conditions. So, this is how we are going to make a choice of barrier and the control strategy, that given the safe region, we will try to define the barrier function, and we will try to see that well that this necessary and sufficient condition of safety invariance is satisfied. Okay. That means the sublevel set of this is, because essentially what are we doing? We are creating the barrier function in such a way, you are given the safe set, let us say, right. You are, let us say you are given the safe set. What is the target safe set? You choose the safe set, your barrier defining safe set as a subset of that. Okay. And what you do is you ensure that the sublevel sets of your barrier defining function is safe and invariant. That means whatever is given an S as S, that you need to be in this S, you restrict your trajectory to a smaller part or maybe the full part of S, and you define the barrier function in such a way that this entire S that you have defined is a sublevel set or up to the 0 set. So, if you remember, 0 set means where the barrier function value is 0, the sublevel means the barrier function value is negative, the super level means the barrier function value is the function value is positive. That is how these sets are defined. So, what we just did, let me just repeat, this is my entire allowed region, the green region. I said that okay, I will let my system to only belong inside this region, not even in these green regions. And how am I doing it is, I am defining a barrier function so that this my target safety region is contained inside this 0 level set and the sublevel sets. Okay. That means whenever my system is moving around in these points, what is happening is that the corresponding barrier values are either located on this surface, the 0 set, or they are located inside this, that means inside any of these sublevel sets. So, these are the sublevel sets, right. That means collection of points on the surface, but all those values are negative, the B values are all negative downstream, right. But the next thing we need to ensure is, well, we should not forget the control. The control cannot be abrupt, right. The system's control should ensure that the system is smooth. It smoothly steers the system's movement trajectory and also prevents it from becoming unsafe, right. So, that means it will discourage the value of B x u from becoming positive, and also if you remember our earlier ideas of smooth control design, that the control input should not vary abruptly, that also we need to see. Okay. So, with these things in mind, what we will do is we will first extend our definition of the Lyapunov function. If you remember what the Lyapunov function was doing, it was ensuring stability. We will define something called a control Lyapunov function, which is doing the same thing, but for the control system. That means the closed loop including the controller. So, it is basically the same thing. Why are we coming with this thing? Because not only the designing the control needs to ensure safety as an invariance of the system, but also we have to ensure its performance, smoothness, etc., and stability, right. So, for this we bring in the control Lyapunov function. It is almost similar as the normal Lyapunov function. As you can see that V is a function like this, it is continuously differentiable and it has bounded sublevel sets, right. That means what I mean for any value of C. So, if you remember that V x equal to C for all values of x for which V x equal to C are its I mean level sets for x equal to C. Sublevel sets mean sublevel sets for any value C means all values for which V x less than equal to C. And we are saying that this is continuously differentiable and it has bounded sublevel sets. That means all these sublevel sets are invariant for the function. That means let the system start with some valuation V which is less than some value C. the design of the function must be such that it will always be inside, it will always be satisfying this Vx equal to c. That means every sublevel set would be invariant. Now, how do we really ensure that? We ensure that in a way which is very standard in Lyapunov function definition. We ensure that at the equilibrium point the value is 0, at xc the equilibrium point, or v0 equal to 0, assuming 0 is the equilibrium point. In general, v is always positive, and for all the other values of the positions apart from the equilibrium point, we have this condition. The condition is this, that this del v del x times fx plus del v del x times gxu is less than or equal to some gamma times Vx. Now, see, this is a bit tricky, right? Why do I suddenly have something like this? If you remember our conditions of the original Lyapunov function, they were like Vx is greater than 0, v dot x was less than or equal to 0, right, and v0 was equal to 0, right. So, that it was something like that. Essentially, we have the same thing here. The difference is, see, now we have Vx greater than 0, v at the equilibrium equal to 0, and if you remember, we need the time derivative to be negative, right. But now we are talking about the control system. So, instead of having x dot equal to fx, we have fx plus gxu. That means the control input is also there, right. So, when we take the derivative of the Lyapunov function, right, you take dv dt, what you have is del v del x times del x del t, right. Now, that would give you this del v del x. If you take f dot x dot, now x dot is not only fx, right. So, you have fx plus you have del v del x times this other part which is gx times u. So, that is what we are writing. The original definition of Lyapunov function had this thing as negative, right. We want that in a different way. So, what we are saying is not only is this negative, it cannot be, it is not only any negative value, but let me give a bound that how much negative it is at different positions of the space. Okay. So, what it really means, let us understand. So, to give it, to have some control on this Lyapunov function's value, we write minus gamma, right, times the value of Vx. So, if I now just write it in a simple way, essentially we are saying this entire thing, if you write this equation, this entire thing, it is saying nothing but the time derivative of x is less than or equal to minus gamma times Vx. This equation looks something like an exponential decay, right. So, that means we are saying that, well, the Lyapunov function's value must decrease, and this value of gamma being a positive value, is a parameter which is helping the designer to choose in what trajectory of exponential decay the Lyapunov function's value will decrease. Let us understand this again. If you just say v dot x is less than 0, that means you are just ensuring that, well, it is negative. But I want to have some control over the performance of the system. So, I want to say that, well, it will not only decrease, it will decrease at some rate that I choose. So, I say that, well, let it decrease exponentially with a rate that is gamma. Now, to ensure that I actually give the exponential decay parameter, and I make the parameter as minus gamma times Vx, because if this is so, now if you solve this inequality, you will see that the value of V will be decreasing exponentially with this gamma as the rate of exponential decay. Okay. So, essentially what we are doing is, we are not only now choosing the Lyapunov function, we are choosing the Lyapunov function as a function of both x and u, and we are going to say that, well, let the control design method give me an value of u, so that this inequality is satisfied. Ultimately, what is the control design method? It is a optimization problem, and all we are doing is we are adding constraints on the optimization problem, so that certain performance conditions are satisfied. So, here the performance condition that is satisfied is, we are forcing the u to be such that this equation is satisfied. If this equation is satisfied, v will decrease along the trajectory of the system following an exponential decay, which in effect will give me a control on how smoothly, how fast the system approaches its equilibrium point, right. So that's the idea here. So this V that we have defined here as a function of both x and u along with this parameter gamma for smoothness is known as a control Lyapunov function. Okay. So if we clear a control strategy now, my control strategy can be defined like this. It is defined based on this control Lyapunov function that, well, let me choose a u so that this thing is satisfied. If this thing is satisfied for a given u, then I am ensuring that smoothness factor is there. So fine, let's proceed. So this is about performance, and now we have already earlier talked about safety. Now all we will do is we will punch these two things together. But before doing that, let's just have a pictorial view of this Lyapunov function. So like I said, what we are ensuring is, well, this is my Lyapunov function, right? And this is a picture of a Lyapunov function that we want it to be something like this. Why like this? It is always positive, right? I mean, again, I am allowing the system to veer on the surface of this this blue shape, like an inverted igloo, let's say, or it's like a cup here. What we are ensuring is that the system's trajectory is always on this surface. Okay. Now, if you see this white circle, it's a sublevel set of some initial value x. Okay. That means from here all the values will go to be below that value of x. Okay. And the CLF will decay along the trajectory because the derivative is negative. Okay. Now, if it is negative, then, well, I will always come down like this, I will be moving around on the surface of the system. Okay. So let's see the difference that how having the gamma parameter helped me here. So it helps me to make this decay of the Lyapunov function stricter, like I said, that it is not only negative, it is not only decaying, it is decaying at a given rate. And this is what we call as, I mean, we are ensuring exponential stability with the rate of decay given by gamma, rate of exponential decay given by gamma, instead of just giving this, which was for asymptotic stability. So in picture, if you see that this is the exponential decay envelope with the parameter gamma. So this is ensuring that while the system is decaying within this envelope, if I have exponential stability here, and had it been asymptotic stability, it could have gone out like this, right? But still, well, eventually it's decreasing, but it may happen that it is not decreasing at this rate exponential of the exponential decay that I wanted. Okay. So that's the difference, and this is how with control Lyapunov function, not only I have this shape of the Lyapunov function, but also I am able to ensure that, well, I decay at a rate that I choose, and the rate is exponential. Okay. So that's about the stability and performance. I am able to ensure by using a suitable control Lyapunov function that how smoothly the system will approach its equilibrium point. Okay. But still, if I just use this thing, there is no guarantee that I will be safe, because as you can see that, well, if I just use this, well, my system has no guarantee that it can start anywhere in the initial point, right, for which the control Lyapunov function's value, let's say I am starting here, because this is a valid initial point, right. So here my control Lyapunov function's value is this. Now let's say I am moving inside like this. So essentially what is happening is the control Lyapunov function's value is kind of decreasing, right. As you can see that as my system, so this is where I am plotting the x1 comma x2, right. As my x1 x2 is changing, I am moving like this. Let's say my control Lyapunov function's value is moving like this. Of course, it is positive, but it is decreasing, and if I plot it here, the value of v as a function of time, if I plot it, you see that, well, it is decreasing like this, and somehow we are able to also guarantee that it is satisfying this rate of decay, because with that only I am enforcing the constant. Fine. So fine, we understand how to give the Lyapunov function a parameter, and how to make the Lyapunov function sensitive to both x and u. So now how about this safe control strategy? So let's understand one thing. for Lyapunov function, all the subsets, all these sublevel sets, they are all invariant. That means, if I make my system start here at some Vx less than c, it will always be there. Any subset is invariant. But for the safety requirement, I don't need that for the barrier function all the sublevel sets of the barrier function are invariants. That okay. I only need the barrier function the 0 level set, which is ensuring the safety, to be invariant. Let us understand what I mean. When I am having this Lyapunov function, suppose I choose any set, okay, for sublevel set of some value x less than c. Suppose this height is c, c1, let us say. So, this is my level set for this entire thing below this red circle is my sublevel set for c1. Similarly, let us say this is c2. This circle, everything below this circle is the sublevel set for c2. So, the Lyapunov function guarantees that, well, if you start somewhere below c1, you will always be below c1. If you start somewhere below c2, you will always be below c2. I do not want those things to happen for the barrier function. Those are, if they happen, they are fine, but that is not my requirement. My only requirement for the barrier function is that, well, when I am satisfying the safety, I should always be safe. That means what? That means this is my 0 level set. All the the sublevel set of this 0 level set should be an invariant. I should never go here, and if I start anywhere here, if I start anywhere inside this, I should always be inside this. That is all I want, because then it automatically guarantees that I never come here. So, let us see that how we come with that requirement. So, what we do is we choose a barrier value so that this thing is satisfied. Now, let us see what does this mean. So, we are saying that lambda is a positive quantity and b dot is less than equal to some lambda v. Okay. Now, there is a issue here, you need to understand. See, initially my b is negative, right? I allow my b to be negative inside the safe set. Now, if this is negative and I have lambda which is positive, and here I have a negative sign, that means b dot is allowed to be positive. Is that okay? Why this is okay? Let us understand. Like I said, that I only want my system to be inside this, only this should be my invariant region, right? I want to guarantee that. That means I am fine with allowing the system's value, the barrier function's value to increase as long as I do not cross the boundary, right? It is not that I always want the barrier function's value to decrease. That is my point. If it decreases, that is fine. It is negative. So, it is as long as b dot is less than some positive value c, it can be positive up to c, but also it can be negative, right? So, it can decrease, but what I am saying is only this is the invariant set. That means I do not need b to always decrease. It can sometimes increase, but the only thing I need is it should not increase when it comes here. It should not increase beyond the 0 level set. That is what I want. How do I ensure that? Very simple. We use this kind of a constraint. It is helping me, you see, as long as b is negative, the value of barrier itself is negative, right? As long as the value of barrier itself is negative, that means I am somewhere here. I am saying that the derivative is less than a positive value. That means the derivative can be negative as well as positive. That means I can be anywhere here, I can increase, but when shall I stop increasing? See, the moment I reach to b equal to 0, this b dot becomes forced to be less than equal to 0. Okay. So, in summary, I can say this, that I am allowing b to increase as long as b is negative, but as b approaches 0, b dot also approaches 0. That means once I am approaching this boundary, I am not allowing b to increase, and once, if somehow I cross this boundary, again this derivative will be negative, so b will decrease, right. So, if I choose, so if you recall our earlier barrier function definition, we said that, well, let b dot be always negative.
Just like we introduce the parameter gamma for the control Lyapunov function, for the control barrier function, I want control, right? I want to control that how smoothly the system approaches the safety boundary. So, similarly, I introduce this parameter. It is ensuring that, well, I can grow, but I can grow only up to the safety boundary. I will not cross it. The moment I cross it, the barrier function's sign will change. Immediately, the gradient will become negative. Immediately, I have to get back to the system, right? So, in this way, I am constrained to be inside the safe set, and only this 0 levels, I mean sub-level sets of 0 level set of 0 is my invariant. That is what we are able to constrain here. Okay. So, suppose I did not have this thing, I just had b dot less than 0. What would have happened? It would have happened that my safety enforcement would have been abrupt. That means, I may have gone like this and immediately I came down, right. But now, I introduce this smoothness parameter lambda. That means, with this I am how the barrier function's value is changing, it is not abrupt. It is not abrupt like this. I have a control here, right. So, as I approach the safety boundary, my barrier function's value will change smoothly like this. Okay. So, that is my point. I mean, I am able to force the smoothness on this system, and it is not changing in this kind of abrupt way. Okay. So, using this, I am bounding the positive slope inside this sub-level set of B0, and it will gradually reduce the value of B as it approaches 0. There will be no sudden change. Since there is no sudden change, the control will be smooth, and the guidance of the system would also be smooth in that way. So, fine, let us proceed from here. So, this is how we define the control barrier function then, right, that, well, it is a function which just like the Lyapunov function will satisfy this condition, but you see minus lambda b, this is what it requires. Okay. There exists this positive lambda, so that this happens. Okay. So, if I want to ensure that my control value is such that it satisfies the safety requirement, then my control strategy would be such that I should always choose a u that this gets satisfied. So, that I am able to smoothly control the value of the barrier function and keep it inside the safety region. So, this is ensuring that this is negative inside S, and it is in the limiting condition when I approach the boundary, this becomes 0 with this decay rate, right, and outside it is definitely positive. Okay. So, that is the trick, and I hope with this most of the understanding is clear, and then all it depends is we need to combine them. We have already seen that how to create a quadratic cost function in LQR. We similarly create this kind of a quadratic cost function again. So, we say that, well, what we want to do is we want to generate a u so that this summation is minimized. Okay. It is basically like the something like the older LQR thing, right. So, quadratic term over the control, and there is also this slack term. We will see what this slack term means. We want to minimize these things subject to constraints. The first constraint is the barrier function. The second constraint is the Lyapunov function. You see, inside the Lyapunov function, we add some small delta value, which is also here. This is called a slack variable. It relaxes the constraints, because if you can understand that in the Lyapunov function, I mean, if I just force the Lyapunov function, all the sub-level sets, they are also invariant, right. So, I can actually relax the constraint there, but for safety, no such relaxation is done. We do not give any relaxation on the safety. The moment I am approaching the safety boundary, I must go back, right. So, there is no slack variable here. I do not relax this constraint, but here I have this as a tuning parameter. When I am doing this control design, I can choose delta, so that, well, finally, here the Lyapunov function is giving me an exponential decay performance. I can have some relaxation over it. Okay. So, this is how we define the control and also make it safe here. Okay. So, the objective is non-linear and quadratic, like you see, and also you can use some well known quadratic programming solvers to solve this non-linear optimization problem, and safety is enforced by the CBF, and the performance is enforced here by the exponential decay of the control Lyapunov function. So, if you take that harmonic oscillator example again, and if you create this kind of a domain of the system, if you give an unsafe set here, So, if you see that, well, this is my unsafe region specification, it is given here. Let the this is my entire domain x1 belonging to 0 to 3 like that. Well, it is somewhere here, and for this system let us assume these two functions. This is my CLF and this is my CBF. This has been taken from this example here, and also our treatment of the control Lyapunov and control barrier function was taken from a paper by Sam Coogan et al. I think we have already referred that earlier. If you see the references are right here, this is the reference by Magnus, Ørsted and others, Aaron MS and Coogan. Yeah, Magnus, Ørsted, Paul Tabaudas, ECC 2019 paper. So, here we actually see this example taken from this reference, and we see that, well, if we consider this candidate's Lyapunov function and barrier function for I mean here for this we can show that, well, how the system's trajectory is satisfying the given constraints. Okay. So, you can actually see that, well, the system is moving around, and I mean if you do a control synthesis for this, the system will be moving around. By the way, this is a capital I, right, because this is the unsafe region. Okay. And here we have the system moving around, but it is never going inside the unsafe region as we see. So, let us take an ACC example, a cruise control example, usual set of equations with the control input being the wheel force that you want to give, okay, and also the rolling resistance equation is given like this. And let us say you have an unsafe region, so that which is the unsafe region is specified like this, okay. And for this system, let us say you create a Lyapunov function given like this, v minus vd square, okay, where the desired speed Vd is given like this, okay, and you have this as your CBF, okay. All the usual parameters are specified, mass is given, G value is given, U is the wheel force, and Fw, this parameter is inside this range, and also the rolling resistance is given by this equation. So, this is from this example, this paper actually you can just see. So, what will you see that, well, if you plot the barrier function, it looks like this. So, it is like the front of a ship, right, a submerged ship. This is the water body, this is a submerged ship, right, and here this you want to be inside this 0 level downstream, right, okay. And if you do the constant optimization that we discussed earlier, you will see that, well, for this system, if I am running the ACC using a controller which has been designed using a quadratic programming like we formulation like we discussed here, you see that, well, even so if I plot the distance to the desired spacing, that means what is the, I mean, let us say I have said that the spacing from the lead vehicle should be 0. I mean, it is not ideal, of course. You say that it is really approaching, I am almost reaching the lead vehicle here, okay, and I give a set speed, I am reaching the target set speed here, okay. And if you see here what happens to the CBF, right, you see that the CBF is approaching the safe region, but it is never crossing the boundary, the safety boundary, it is never crossing the 0, okay. Similarly, we have a plot for the other things also. So, well, actually if you see this paper, they have an implementation available, you can download and check, but during our tutorials and examples we will actually show you with inside our assignments that, well, how to solve this optimization problem and how to generate these plots. We will actually give you an example of that, how to do all those things. You will be able to do them by yourself using suitable guidelines that we provide you inside the weekly assignment. Thank you for your attention. We will end this lecture.